So we'll start talking about section 4.2. The unit circle is 4.2 is a unit circle. So we did a little bit with it yesterday. We'll talk about it, and then we'll go over our homework, and then we'll talk about it a little more. So 4.2, the unit circle. So important facts. Yes, question?
So is the unit circle stuff going to be on the quiz class?
There is a little bit of unit circle stuff on the quiz. What I will do is I will have this unit circle projected on the board. So it's just going to ask questions, maybe a couple of questions similar to what we'll talk about on the homework from last night and what we'll talk about today. So the unit circle is a small portion. Small portion.
What is this quiz mostly going to be on? The trigonometry?
4.1 through 4.3. So right angle trigonometry, angles, radians, arc length, the stuff that we talked about in section 1, the right angle trigonometry that we did from section 3, and a little bit on the unit circle. Yes?
Are we going to have a review assignment?
Usually on quizzes, I don't have a review assignment for quizzes. Usually I have a review assignment for tests. So to review, just I would look over what we did in 4.1 through 4.3. Okay? Other questions? All right. So important facts. Our unit circle, we call it the unit circle because the radius is 1. So the radius of our circle is 1, so the hypotenuse of each of our special right triangles is 1. And that's what makes it work out nicely. We're saying the center is at 0, 0. So we put the center of our unit circles at 0, 0. So we can talk about the points around the unit circle. And what we did with our activity yesterday was we put our special right triangles on the unit circle, and we labeled the point where the corner, this one vertex of our triangle touched the unit circle. And we got the x-coordinate from the side of our triangle that was along the x-axis, and we got our y-coordinate from the side of the triangle that went up from the x-axis. So these numbers come from the sides of those special right triangles. And since the radius is 1, the hypotenuse of our special right triangles is 1, we can say that the x-coordinate on the unit circle is the cosine of the angle, and the y-coordinate is the sine of the angle. So if we're talking about some angle, and if I draw just a quick sketch here, if this is my unit circle, and there's my angle. This side is y, and this side is x. So the sides of those triangles are the x-coordinate and the y-coordinate. My radius is 1, so my sine and cosine just come from the y-coordinate and the x-coordinate. That's really the benefit of the unit circle, is that it gives us a way to find the sine and cosine of an angle easily. And we're going to extend that today, but this is really the foundation of the unit circle. So, given this, with this unit circle, let's look at those problems on your blue homework sheet. So number 1 asks us the sine of 150 degrees. So I'm going to go over here to 150 degrees on my unit circle. The sine of the angle is the y-coordinate. So the sine of 150 degrees is 1/2. And that's the answer. That's all we have to do for that. We're just looking for if we're looking for the sine of the angle, we're looking for the y-coordinate. We're looking for the cosine, we're looking for the x-coordinate. So let's look at cosine of 5 pi over 6. Come around here, 5 pi over 6. The cosine is the x-coordinate. Negative square root of 3 over 2. That's all we have to do on the unit circle. Now for number 3, we have to work a little harder. Number 3 says the tangent of 330 degrees. So I'm going to go around to 330 degrees. The tangent of an angle is the sine of the angle divided by the cosine of the angle. Well, the sine of 330 degrees is minus 1/2. The cosine is square root of 3 over 2. So I'm just dividing negative 1/2 by the square root of 3 over 2. I'm going to write that up here. Negative 1/2 divided by the square root of 3 over 2. I can multiply by the reciprocal to divide that fraction. So the 2's cancel, and I get that that equals negative 1 over the square root of 3. And I rationalize that denominator, and I get negative square root of 3 over 3. And I have the exact answer of the tangent of 330. Yeah, thanks. Number 2 was the cosine of 5 pi over 6. So I went over here to 5 pi over 6. The cosine is the x-coordinate. Just negative square root of 3 over 2. The number 4, the cosecant of pi over 4. Well, first thing we need to remember is how do we define the cosecant of an angle? 1 over sine. So cosecant is 1 over sine. So what we're looking for is the sine of pi over 4, and I'm going to take the reciprocal of that. So I'm going here to pi over 4. The sine is the y-coordinate, square root of 2 over 2. And the cosecant of that angle, we take the reciprocal. So we have 2 divided by the square root of 2. And then we would rationalize that denominator. Let me look at another. I'm not going to go through every single one, but are you starting to get the idea of how we use the unit circle? X-coordinate is the cosine of the angle, y-coordinate is the sine of the angle. Yes?
So that one that you just went over, would it just end up being 2 then?
What do we say it was? Square root of 2 over 2, and we do the reciprocal. So we do, I think it just turns out it's square root of 2. Right, so 2 over square root of 2, rationalize that. So we get 2 square root of 2 over 2, and those cancel and it turns into square root of 2. Yes? Yes. So let me do a couple more and then I'll get to number 12. So let's look at number 7. So number 7 gives us a negative angle. And what do we say a negative angle meant? Go, instead of counterclockwise, go clockwise. So number 7 says sine of negative 30 degrees. So I'm going 30 degrees this direction. So I go 30 degrees go in the counterclockwise direction. And I'm looking for the sine. So that is the y-coordinate, minus 1/2. So that's all I have to do for that one. Number 12. Someone asked about number 12. The cotangent of 7 pi over 4. First of all, let's remember how we define the cotangent of an angle. What is it, Colin? 1 over tangent. So we're taking the reciprocal of the tangent. So what we're looking for is to find the cotangent. We could do it 2 ways. We could find the tangent and take the reciprocal, or we could remember that the cotangent is cosine over sine of the angle. So let's go to 7 pi over 4. So here we are, 5 pi over 4, 7 pi over 4. And we're going to do the cosine divided by the sine. The cosine is square root of 2 over 2, divided by the sine, negative square root of 2 over 2. So what do we get? Negative 1. And that's it. All right, let's look at a couple from 13 through 16, because those are going the opposite direction. So for number 13, it says at what angles is the sine of the angle 0? So what that question is asking us is on our unit circle, where is the y coordinate? The sine of the angle is the y coordinate. Where is the y coordinate 0? So I look at my unit circle and I see a y coordinate of 0 here. And I go around here and I see a y coordinate of 0 here. So the angle that gives us a sine of 0 is 0 and pi. That's where the y coordinate is 0. Number 14 says what angle in radians gives us a cosine of 0? Number 14. What angle in radians gives us a cosine of 0? Cosine is the x-coordinate. So I'm looking on my unit circle where the x-coordinate is 0. I have one here, and I have one down here. So I have pi over 2 and 3 pi over 2. Those are the angles where the sine, or I'm sorry, where the cosine of the angle is 0. And then let's look at number 16. It asks us what angle in radians is the cosecant of the angle undefined. So let's remember what the cosecant of an angle is. How did we define the cosecant?
1 over sine.
1 over sine. So where is the fraction 1 over sine theta going to be undefined? Because the sine of theta is 0. So that makes us divide by 0 there. So we're looking for the sine of the angle being 0, and that is at 0 and at pi. So that's a little taste of how we use the unit circle. That start painting a little clearer picture of how we use the unit circle. Okay. We will practice with this more. So if it's not making 100% total sense, don't get frustrated. Stick with it, and it'll start to come together. We'll practice with this more. All right. So not going to collect this. If you have other questions on this worksheet, come and see me. We'll go over them. But hopefully that gives you an idea of how your unit circle works. On quizzes and tests, I will give you, or I'll project something. I will give you, unless I'm asking you to memorize some of these, I would give you a unit circle that looked like this, so you had 100% accurate information, just in case you had a minus sign where you shouldn't or something on your own paper. So everybody has the exact same information. Okay? So, questions before we move on with the unit circle. So this is the basics of the unit circle. The really nice thing about the unit circle is it lets us extend our ideas of trig functions. So what I want you to do next is visualize. So we're going to extend the trig functions, because so far we've been talking about sines and cosines of angles, and it has to do with triangles. But what the unit circle lets us do is extend that definition, and it's kind of a cool idea. So here's my circle. Michael is not in here now. So there's our unit circle. And what we're going to do is, here's my center, and I'm just going to draw in my axes, my 0 degrees and my 90 degrees. Now what I want you to do is visualize, imagine that we're connecting a number line to this point right here. So I'm going to extend the number line out from this point 1, 0. And now what I'm going to do is we're going to imagine that this number line And here are my numbers on my number line. Imagine this number line is flexible. So I'm going to pick up the number line, and I'm going to start wrapping it around the unit circle. So my points end up around here. And eventually, as I wrap the number line around the unit circle, I'm going to draw another little picture down here. I won't put as much detail. I will wrap that number line tightly around the unit circle so that each number on the number line matches up with a point on that unit circle as I wrap it around. Now what this lets us do is we can think now of the sine and the cosine of any real number, because I just wrap this line around the circle. When I get all the way around once, I just start over again. So every point is going to be touching at some point. We're imagining our number line isn't thick, so it doesn't wind up bigger and bigger. So every point on our number line is going to touch some point on our unit circle. So these real numbers aren't necessarily angles. They're just a number. So it lets us think about finding the trig function, sine, cosine, tangent, cosecant, whatever, of just a real number. It doesn't have to be an angle in a triangle. And when I wrap this point on the unit circle, the sine of that point on my number line is the x-coordinate, and the sine of that, or the sine is the y-coordinate, and the cosine of that point is the x-coordinate, just like we did for our special right triangles. So if I have some number here, it's at some point on the unit circle, I can find the x and y coordinates, and we call that the sine and the cosine of that point. We're not even talking about angles anymore. We're just talking about a point. So we're letting our trig functions operate on real numbers, not just angles. So that's a nice benefit of the unit circle, is it lets us extend this idea of trig functions. So an example of this, the type of problem that you might see, is you might be asked to evaluate the 6 trig functions for the real number t equals pi over 3. So this is just some number. So what I'm going to do is, and normally if you're using the unit circle, they're going to give you nice numbers where you can read these numbers straight off the unit circle. So looking at our unit circle, I'm going to say that the sine of pi over 3 is what? You look at your unit circle, square root of 3 over 2. So if we have some real number on our number line corresponding to pi over 3, some x equals pi over 3 or t equals pi over 3, we can find the sine of pi over 3 with square root of 3 over 2. The cosine of pi over 3 is what? From your unit circle. 1/2. We're just looking at the x-coordinate. So the point pi over 3 on our real number line corresponds to square root of 3 over 2 and 1/2 on our unit circle. Our xy on our unit circle is square root of 3 over 2 and 1/2. And we could go on if we wanted and find the rest of the 6 trig functions. We could find the tangent by dividing the sine by the cosine. We could find the cosecant by taking the reciprocal of the sine. We could find the secant by taking the reciprocal of the cosine. So from here, we could find all 6 of our trig functions for this point. Once we know the sine and the cosine, we can go on then and find all six trig functions. Yes. Oh yes, thank you. I wrote these backwards. I switched my xy's. Thank you. So when it asks us for the values of the trig functions for a number, we're just looking on our unit circle. The sine is the y-coordinate, the cosine is the x-coordinate. That's all it's asking us to do. And if it asks us what point it corresponds to, it's just going to correspond to the point cosine, sine. That's all the question's asking us. Questions on that? So I hope that we're starting to see a little bit of how we use the unit circle. All right, one other thing that we need to talk about for sine and cosine, what we're going to get into in the next section in 4.4 that will start on Friday, is what the graph of the sine function and the cosine function look like and how we work with those graphs. So we're going to talk about the domain and the period. Since we're talking about plugging a real number into the sine and the cosine, not necessarily an angle, just any number, we can think of the sine and cosine as a function. And we're going to start thinking about it as a function, and where we can plug any number in there. So we want to talk about the domain and the period. This is still 4.2. So we're still in 4.2. We're just talking about some things that we can figure out from all of these things, or we can figure out from the unit circle. So if we think of wrapping the number line around the unit circle, and if we're thinking about negative numbers, we're just going around the opposite way. What do you think the domain of the sine and cosine are going to be? I have that number line, and I can just keep wrapping it around and around and around as long as I want. So what do we think the domain is going to be? What values could we plug into the function? Is there going to be any restriction for sine and cosine? What do you think, Nancy? Those are just going to give me zeros, right? We're not talking about the cosecant or the secant. We're just talking about sine and cosine. So are there any numbers that give us a problem if we plug it into sine and cosine? Can't I just keep wrapping that number line around and around and around the unit circle as long as I want? Positive direction, negative direction. So the domain of sine and cosine are negative infinity to infinity. So our domain is negative infinity to infinity, or I could write this as negative infinity less than or equal to x. I guess it can't be equal. Less than x, less than infinity. If we're thinking of plugging the next value. And our range. Looking at our unit circle, let's go back. I'm going to go back to our unit circle here. Looking at our unit circle. If we think of, let's look at the cosine. The cosine starts at 1. It goes from 1, it goes square root of 3 over 2, square root of 2 over 2, 1/2. And then here at the y-axis, the cosine is 0. So it starts at 1, it goes to 0. Now it goes negative Negative 1/2, negative square root of 2 over 2, negative square root of 3 over 2. Now it's at negative 1. And down here at the negative y-axis, it goes back to 0. And as I go around again, it goes back to 1. So what's going to be the range of the cosine? It goes from negative 1, that's the smallest it gets, and positive 1 is the biggest it gets. So the range of cosine is negative 1 to 1. Now let's look at the sine. Sine is my y-coordinates, goes from 0 around here, goes up to 1 here, and now it goes back down to 0. So I went from 1 up to 0, from 0 up to 1, back to 0. Now I go around, now I'm at negative 1, and back to 0. It's the same thing. The range of sine and cosine are negative 1 to 1. So when you plug a number into the sine function or the cosine function, the biggest number you can get is 1, the smallest number you can get is negative 1. Negative 1 less than or equal to x less than or equal to 1. And the way we write that in interval notation is negative 1, 1, and I would put brackets this way. The square brackets mean equal, the round brackets mean less than or greater than. The other thing we can see from our unit circle is if we keep going around, we keep getting the same numbers over and over and over again, between -1 and 1, and between, for both of these. If we keep wrapping our number line around, we don't get anything other than the numbers between -1 and 1. So we say that the sine and the cosine are periodic. Sine and cosine are periodic. Periodic just means it repeats. Over a certain interval, over a certain values for x that we plug in, our function repeats. That's what periodic means. So our period of our sine and cosine, if we go around the unit circle, we go around once, we get all the values between -1 and 1, and then we start around again. So when we go all the way around the unit circle, how far in radians have we gone around? 2 pi. We've gone around 2 pi radians. And then it repeats again. I get the same numbers for sine and cosine as I repeat. So we say the period of the sine and the cosine is 2 pi. Every 2 pi units, I start getting the same numbers back again. So the period of the sine and cosine is 2 pi. Or any multiple. So if I went around 4 pi, or 6 pi, or 8 pi, any multiple of 2 pi, if I go around more times, I still get the same numbers. The way we write that is that we say that the sine of 2n pi plus t equals the sine of t. So any multiple of 2 pi that I add to my angle, I get the same number as if I just had the original angle. So adding a multiple of 2 pi is just like going around the circle an extra time. So I go around the circle to the same place. And the 2n pi makes sure I go around the whole time. And I can say the same thing for the cosine. The cosine of 2n pi.
Is n the amount of time he's going around the circle?
And I'll make that in just a second. I'll make that clear. So n equals 1, 2, 3, and that's the number of times it goes around the circle. Yes, so that's exactly right. So n can be any number. We're just going around the circle. It could be negative also. I could go around the opposite direction. But that just tells us how many times I've gone around the circle to get back to the same point. So this is how we say that our function in symbols, this is how we say our function is periodic and the period is 2 pi. So these two are what happens when we have a periodic function. 2 pi is our period, n is just the number of times we're going around the circle. T is just our number. T is just the number that we're plugging into the function. We're using t instead of x. It's just kind of traditional in trigonometry to use t instead of x, but we could use x also. One other thing that I want to make about the sine and cosine function, then we'll do an example, and then we're done. So other important facts about the sine and the cosine functions is that they're even and odd. One is even and one is odd. So even and odd, let us simplify some things that we do with our trig functions. Cosine theta and secant theta are even functions. Does anybody remember what we mean when we say an even function? It has to do with using negative x instead of x. Let me give you a hint. X squared, y equals x squared, is an even function. Did that help you out? So that wasn't the part of x squared that I was looking at. What an even function tells us is cosine being even means that cosine of negative theta equals a cosine of theta. So if I plug in the negative of my angle, it's the same as the positive. So y equals x squared, if I plug in positive 2 or negative 2 into y equals x squared, I get positive 4 for both of those. So that's why x squared is positive. So cosine of theta is positive also. If I plug in a negative angle, it's the same as the cosine of the positive angle. And it's the same for the secant. Secant of negative theta equals the secant of the positive angle. So if we have some negative angle in here, we can say it's the same as the positive angle. The other trig functions are odd. And by odd, that means that, for example, the sine of negative theta is the opposite of the sine of theta. We change the sign. We plug in a negative number. If we change the sign on our angle, that changes the sign of our function. Tangent of minus theta, negative theta, is negative tangent theta. Same for our other trig functions. And the cotangent is the same. So if we remember these even and odd things, it can help us, it can simplify our work if we have some negative angle inside our function. We can remember that either it doesn't change the sign of anything or it just changes it to the opposite sign. So cosine and secant are even, sine, tangent, cosecant, cotangent are odd. All right, are we good with that? So let me do one example of a problem that usually trips people up a little bit. And then we'll work on homework. So our example, we want to use the period to evaluate the cosine of 5 pi. So what this question is asking us is, can we write 5 pi? We know that the period is 2 pi. We want to write 5 pi as some multiple of 2 pi plus some other angle. Because if I have a multiple of 2 pi, that just means I'm going around the circle again and I don't have to worry about that. So how could we rewrite cosine of 5 pi as a multiple of 2 pi plus some other angle? Well, what's the closest multiple of 2 pi to 5 pi? 4 pi. So we're going to write this as 4 pi plus what? Pi. This is the cosine of 4 pi plus pi. Well, the cosine of 4 pi just means we've gone around the circle twice. That's a multiple of 2 pi. So this is just the same as the cosine of pi. And looking on our unit circle, what's our x-coordinate when we're halfway around the circle? -1. Now you could look at your circle and count. Okay, there's 1 pi, there's 2 pi, there's 3 pi, there's 4 pi, there's 5 pi. So for this problem, you could actually go around the circle and figure it out. But if they gave you what's a cosine of 7,382 pi, it would be kind of hard to count all those times around. So this kind of problem is asking you to rewrite your angle as a multiple of 2 pi plus some other angle. Let's look at a little more complicated one. The sine of 19 pi over 6. We want to use the period of the function to help us evaluate this quantity. So what we want to do, what this is asking us to do, is rewrite this as the sine of some multiple of 2 pi, and we're going to want it as a fraction of something over 6 plus some other angle. So what fraction, how can we make a fraction with 6 as the denominator that's a multiple of 2 pi? What's the first one you can think of? What's our easiest, what fraction can we write with 6 in the denominator that's a multiple of 2 pi? 18 would be 3, but we want an even multiple. 12. So because 12 divided by 6 is 2, right? 12 divided by 6 is 2, so that would give us one time around the circle. So if I write this as 12 pi over 6, 12 pi over 6 is just 2 pi. This is 12 pi over 6 plus what? 7 pi over 6. So I want to split this into two angles where one is a multiple of 2 pi. So think of the easiest multiple of 2 pi you can. And if that's too small, you can make it a little bigger. 12 pi over 6 is just 2 pi, so that just means we've gone around the circle once. So this is the same as the sine of 7 pi over 6. And on our unit circle, we go to 7 pi over 6. What's our y coordinate? Anybody got it? 7 pi over 6? -1/2. So if I go around to I'll go back to the unit circle we had up here. So here's our unit circle. Here's 5 pi over 6. 7 pi over 6 is right here. The y coordinate is -1/2. So when the problem asks you to use the period, you're writing the angle as a multiple of 2 pi plus some other angle. All right, questions? So the homework today is more practice just using your unit circle, some using the period, and also using some even and odd stuff that we talked about as well. All right. I hope we're all feeling a little better about the unit circle now. Page 278. And the quiz tomorrow is not long. So one, if you have questions, I'd recommend come to tutor time. But we will have some time before the quiz to answer some questions if you have questions tomorrow. The quiz shouldn't take the entire block.